We will do chapter 5, diffusion, thermally active process. What we're doing here is that try to understand how strengthen how to strengthen metals. Right. Now, first term is called diffusion. So when we do treatment of materials, we will transfer the mass within liquid, gas, or other solids. So the illustration that you see on the slide here is how the diffusion done. It's like a pool of water, then you add in the dye. So the dye will disperse equally when it reaches. So it's the same procedure as alloy, or try to produce alloy. Mix a small molecule inside the host of the Q1. So in previous chapter 4, even chapter 3, we learned how to calculate the space that needed to fit the alien molecule or extra molecule inside the cubic structure. So today we do a little bit of calculation on how much concentration or how much molecule that we can infuse into the host. So diffusion, by definition, is a phenomenon of material transport by atomic motion. This in terms of actually. So the first one is diffusion couple. So let's say we have two metals, copper and nickel. So when you put these two metals together, so how we represent the copper and nickel before the diffusion, we represent the red dot as copper and blue dot as nickel. So this one is before high temperature heat treatment. So when we heat up the material, we will see some diffusion happen between the two elements here at the boundaries. So the exchange will happen at the boundary first. Like that. Okay. So this is before. So concentration of nickel and copper will be reached 100% before and after. So this is the position. Position x axis from 0 to x here. So 0 x. Then 100% concentration. So you will see that at the middle of the boundaries between the red dot and blue dot, you see that there is 100% there. So when we heat up the two materials, right, for a certain period, and then we cool them to the room temperature, so it will have a change of concentration to the direct flow. What do you think? What will happen? What do you think? If you heat up and cool it down, how you move? Red dot, blue dot will move to the left, red will move to the right. What happened to the concentration at the middle here? Okay, 100%, right? So how it will look like? How it look like? So, how you draw how will it look like if heat up and then you say that it's diffusion at the top. Let's say this is the original. Original is 100%. What happened after you? What happened? What happened to the blue fabric color? Maximum 100%. Both blue and green. What happened in the middle? If you say there's a leadership, how will it look like? No. No line in the middle. No line in the middle means there's a hole there. If you say that there is a hole in the middle like that. And there's a hole here. Morning, sir. This one will look like that. There's a hole between the two and if there's a 0% at the center. What happens if there's a diffusion? How should you draw that? How? You say there's a mix, then how? How you go? Just like. Oh, this is before 100% both at the center. This one box only. A plot line in the middle. After the box, they show have a line in the middle. Yes. Slant the line at the bottom from right. If you empty, it becomes hole already. Two line means if you have this one 0% means there's a hole between the two lines. Dotted line. Two line like that, like the prison one. Just now before mix. Now I ask you after mix, after you raise the temperature and there's a diffusion. One line. Huh? One line. One line. Then what happened to the blue? What happened to the green? Mix. Purple color. Because green and blue become mixed. Same then it's still 100%. 200%. Oh, I agree. Oh. Okay. What happens? Let's say I draw the blue dot. All these are 100%. Right? So 100% your graph will look like that. This is 0, this is x. 0 and x relation. Right? So what if I change, there's some concentration drop. Let's say after heating, the concentration drop. Let's say here, let's say you break into a four section. Let's say here also 100%. But here drop to only 17%. How do you draw that drop? Here come 70, right? Here when we drop to the lid, maybe 60. Maybe so we don't. Right? Which one will be 10%? This is liquid. So this one, you will see that the dropping of the concentration will be like that. It's a red color. Another. Okay, now back to my question. See this one. And you say that there's a diffusion level. How will the graph become? Let's say the green drop, I mean the copper drop. What do you look at that? No, I mean, if there's a diffusion happen, if some red color moves start to move away, so there's some reduce of concentration. Then if this one moves to here, there must be some copper here. So that's why there's some diffusion. Then what happens with the blue color?
Same thing, same. The same.
Color will But one concept you must always remember. What is the concentration that we calculate in the previous chapter? Always what? 400%. Let's say in the solution. What's the concentration even though you mix two material? What you always get? 100%. So here, you get 100%. You get this mark and this mark. You add these two values together, you still get 100%. Here, also 100%. We don't know how many percent, but if you add the two graph together, you get 100%. Okay, so let's say there's a diffusion happen. So means blue dot move to the left, the red dot move to the right. So you look like something like that. So there's some atom move to the left, some atom to the right. And the one that I draw on the whiteboard there is you assume that there is balance when we cure the two element there in a very constant control temperature. Means we heat up, then we slowly cool down. Means we allow there's an energy for the blue dot to move to the left, enough energy, but enough time for the red dot to move. Okay. So we will see something like this, like what I draw on the whiteboard. Okay, not the two lines same side. So whichever two dot that you learn, you measure from the graph, you get total is 100%. Okay, it's only different element. And when you match two material together, just meet on the border, on the far left and the far right, always at 100%. Means the red color 100% on the left, blue color 100% on the right, but the red color is 0%. Blue color on the left will be 0%. Okay. Now there's the mathematics to calculate rate of process in solid. Okay. So diffusion also happen in the pure material. The previous slides you see is a blue material, copper and nickel. But pure metal also can happen pure diffusion by exchanging location of the atoms, like what you see on the speaker. Right, the green dot goes to the left hand side. Okay, so this is a defect. There's a hole there. This is a point defect. So this one, the gray color will move to the left, move to the right, and the B1, you can this one can move these atoms, the one on the top here, you can come and replace this one, and this one can be pulled out from the location and then arrive at this location. This is called self-diffusion. Okay. Now, how it link to your test 2 or final exam question? The question will either ask you explain diffusion by diagram, need to draw, or some after you solve the first part, calculate the space already. Okay, let's say you have a PCC. Calculate the space that you need already. The question asks you how self-diffusion happen in VCC and BCC crystallography. Okay, then I ask you to go and memorize 3 elements from BCC, 3 elements from FCC, and 3 elements from SCP. Right? So, how self-diffusion happen in BCC? You need to remove 3 elements. 3 examples. BCC is a crystal structure. Okay, so there are type of element that is inside BCC. I mean, is having a BCC crystal structure. Okay, now the question for test 2 or final exam might come out like this. Explain how self-diffusion happen in BCC structure or FCC length. Rule. What do you mean by self-diffusion? Same time, same size. So, if this one copper, the replacement will be copper. Oh, no lah, but this one no. But how self-diffusion happen in BCC element? You label this one atom 1, atom 2, then you draw an arrow throughout. This one should to here. Okay, this one will become, draw another one. So this one become O. Then this one, or okay, so other atoms come inside pumpkin. This is also okay. Okay. Now, how you define the rate of atoms move into solid states? We use the graph. On the left, on the y-axis is energy. On the x-axis is coordinate. It's a coordinate. So let's see the few regions. It's more oriented, and the further you move, it's more pronounced. So you have reactant energy and activation energy. Okay, so E star and the product's energy. Energy is to be reacted. So if your energy here when stable and heat it up to reach E star, then you will drop down, you will release. Okay. So proceed with the unreacted on the reacted state. So if your energy stay at here, your atoms will be very stable. And you heat it up, you give it temperature or energy. You will move up to E star by called activation energy. Right. So additional energy required above average energy is called activation energy. So we need to give them a push so that it can move up or move to the left, move to the right, or vibrates, then exchange position. Right? It's like musical hand, right? It's a musical tracings. So the first energy is called reactant energy. Then activation energy and the product energy. So when we have a sufficient energy to react spontaneously to reach the energy, so you need to release the energy until you become the maximum. Okay, you see this more when you learn about the phase cycle. So this reaction is called exothermic. So exothermic means it's given away the energy. Exo means it. Endo is simple. They've got 2 terms. Endo and exo. Exo means give. Endothermic, give away. The exo is give away. Endo is simple. So here's the first equation for today. So you study the effect of temperature, probability linearly related to E power E star minus E stroke KT. E star is activation activity. We have seen E star in chapter 4. And we have seen E star in chapter 3. But in chapter 5, we talk about diffusion. So there's an activation energy for the diffusion. So Boltzmann constant 1.38, 10 power negative 3 joule per Kelvin. Again, Boltzmann had two values. One is in joule, one is in eV. So there is another equation to calculate fraction of atoms. Okay, fraction of atoms. You take n divided by n total. N is number of total molecule with the energy greater than E star. Okay, so what does it mean in the box? Let's say you give the energy, you burn it. The bottom one will be the N star. Means you give the energy to here. If it doesn't move, it's called ER or reactor. So N, capital N total is the total number of molecules present in the system. Inside this case, you have N system. Okay. See another Boltzmann constant here using EV. So don't confuse between the two numbers. One is in joule, one is in. So N divided by capital N total equal to CE exponential minus E star minus E divided by K2. So if you pull this equation inside this equation, right? The two this one inside this equation. So it gives you number of vacancies at both equivalent. Number of vacancy N sub V divided by N equal to C E power minus E V divided by K. So when the question asks you about vacancy, remember to use the activation to form vacancies. Don't confuse the activation energy to do diffusion. So there are a few equations that is important for today. So if you see, if the question asks you to calculate vacancies, you will use this equation. And V divided by N equal to CE minus EV over KT. And the one on the left here, don't confuse with N divided by N total. C E E star minus E stroke K. Don't confuse between the left hand side equation. Okay, let's apply the equation. At equivalent numbers of vacancy per cubic meter for pure copper and 500 degrees. Okay, so how do we find the equivalent number? Which equation we use? That or question asks you the equivalent numbers of vacancy per cubic meter of pure copper at 500 degrees. Use left or right? Right one, the right one, right one. So we use NV divided by N equal to CV minus EV over KT. Temperature here. So you move this equation capital N to the right hand side. So you need to calculate the N first in this kind of structure. How to find N? How to find total number of atoms per site per cubic meter of atoms? How do you find? How you find 1 meter, 1 meter, 1 meter copper? How many atoms inside? The 1 meter, 1 meter, 1 meter. The volume is 1 meter cube. In 1 meter cube, how many copper atoms inside?
Take atom, I'm gonna divide by the one. Okay. I
So there is a table for copper. Copper is for example. Okay. So in the table, you will know where is your A and R relationship. So here, you know that number of Avogadro, right? 6.023 10 power 22. Atom over 1. Number of Avogadro, right? Okay. Over 1. This number equal to 1. Total. How you know how many mole inside? When you're given more volume. How you calculate more? Okay, so there's a equation we convert 1 kilo equal to how many mole? Let's say you have given a copper, 1 kilogram of copper, you have how many mole? Right, you need to have the density of the copper. Density equal to 13 over kilogram. Kilogram over meter cube, right? Think the row volume we can make. Find the load. Okay, use NO rho divided by atom of mass. So you'll be given periodic table. So I assume you already know how to find the atomic mass. In the periodic table, you will see 63.54 gram per atom mass. So number of Avogadro is 6.02 10 power 23. You multiply by density, you will get in 1 meter cube to the 8 10 power 78 atoms per meter. So this is a very popular question for S2 and also for exam. Right? So you substitute the value N here. C is 1. E is exponential plus calculator. EV is given divided by K is Boltzmann. Temperature, remember in Kelvin, although here is Celsius. Right. So normally students fail in this module, they get to change Celsius to Kelvin. The rest we read from science. The rest is the substitution. Next is the rate of reaction. Rate of reaction. If you see E also, but you change the EV into Q, right? You change it to Q divided by RT. We call it Arrhenius rate of equation. Right? Arrhenius rate equation. So this one is popular with you have a chemistry friend, make this equation for. So here, the R value won't be given in the test. 8.3 joule/mole Kelvin. But Q usually so this is um, this equation usually for chemistry has so we need to write m in the log log equation because you want to remove the e here. And once you log both sides, you can pull the minus q divided by RT to the front. We need this operation. Log rate equal to log C minus Q divided by RT. Again, here also remember temperature is Kelvin. So you need to plot log versus log to get a straight line. So the y-axis is log rate, x-axis is log C. This is the plus E, y equal to mx plus 6. So you can plot reference. You plot y equal to log rate. Your x-axis is 1 over t. Log C is your intercept. Y equal to mx plus C of t. So your n is minus q over r. So again, you plot the log rate versus 1 over t. What should the line look like? Go up. Why go up?
Wait.
Why does the negative
Y is 0 and negative should go from down.
minus n? Minus n. So it's
When Y is beginning from
your m is what? Negative value. So it's going to if you plot the one. Okay. So if you want to do just now it's long Ln. If you convert back to log 10, still log 10 is more easier compared to lead. So log 10 rate, but it means the constant value 2.303 per both give you same answer. You can use this one or both give you same answer. It's just a bit of sleep. Right. So this is how a normal experiment data will give you, or just plot experiment data. So on the left is log 10 reaction time or reaction rate. X-axis 1 over t. So the slope will be minus q divided by 2.3 r. So you will intersect at log 10 constant. So once you have a slope, you can do estimation. Once you have y equal to mx plus c, which you can estimate the rate by a certain time. Question with your time, also you can estimate the rate. Then you need to refer to your equation. So you're quite familiar with how the solid, liquid, or gas atoms move. Solid look like this, liquid and gas. So this one we learn for SQL item. So how diffusion happen in metals? Normally they happen if they are already in a solid to solid, then normally it's through temperature and then vibrate, then they will pull into the paper gap. So how diffusion happens in the metals? You need to meet two conditions. One, you must have an empty space there. Like when you do buckling, they must have space. And also they must have energy to break the bond between the material to pull them into the empty space. Okay, there are two things. One, they must be an empty space and there's sufficient energy. Here is the activation energy. It's called activation energy. So diffusion mechanism, there are two: through vacancy or substitution, okay, and installation mechanism. Vacancy, substitution, they must vacancy and substitution, they must meet the Irish rules. It's Irish rules where 50% of the radius of the Irish rules of the Irish rules. Then installation mechanism is the one that owns inside the system. So the one that you see on the screen here is vacancy. How this is move in. This one move here, so this one will left of balance. So if you simulate this one in 3D, you will see the whole actually not the molecule illustration. Actually, it's the atom rather than the vacancy. This one, read, so it's read. So the conclusion for this one is when you raise temperature, you need more energy, the diffusion rate will be higher. Okay, the rest is good. Because all of you are very smart. So it's fun. All right. So this one also unique. So this is the paper, metals, melting point, crystal structures, BCC, alpha ion. Ion is a special material. So when you switch, you increase the temperature, alpha become beta, and at the end it become gamma. So this is illustration of the silicon. So basically, when you see this one, it's appendix. It will ask you chapter 5 question. Why? Because you see activation energy. Right? What's activation energy? Is your EV. The EV. This one is in joule. So when this joule gives the correct Boltzmann value, you have two types of Boltzmann value. One is joule, one is diffuse. Okay. So what happens if you have a hole and the atom want to move to the neighbor? So if you view the graph, energy versus position. So if you want to move from A location 1 to 2, you must give the activation energy so that it move from location 1 to the location. This one is stable or reactant energy. So when it move from here to here, when it reach here already, it's stable. So make sure that your graph come back to the original reactant energy position. Don't stop here. Here you need to still have this still dancing, still party, then it becomes stable. Then to the reactant. Okay. So another one is called the candle effect. So Kukener effect, it shows that diffusion interface most likely to the opposite direction to the most rapid moving species in the binary couple. So if you can see here metal A, metal B, and metal A, metal B here. So here is at start, A is at start of experiment. B is after T, the marker moves in direction opposite, most rapidly pushing into speed. Okay. So A will move to here, like just means that. Again, this is just tell you that you need two factors to make diffusion happen. So even though there are lots of operations happen for this chapter, you only need to remember two things. One, it must be a vacancy for you to park presence. Second one, you must provide the activation energy. For you to happen. Okay, so this is a short video. How canal calendar effect. So you will see that this is a silver manipulation happen. Silver and gold. Silver and gold. Silver is a black, the surrounding is a gold. This one is very, very small, in 100 nanometer. So what does it happen? The black color is a silver. The gold go and attack the silver. There's a space which attack the outer layer and the outer layer space. Okay, so this is how candle effect happen. Okay, so just now I showed you the vacancy and substitution mechanism. Now we go into interstitial mechanism. So interstitial means that we find a space to slot in. Okay, so only the differences between vacancy and interstitial is the size of the Allen angle. So I'll show you what this is the substitution. Substitution is something like this. We will replace the same atoms by meeting the RH rules or Holmes rules. By interstitial, the size will show shorter, smaller than the space available. So as you can see, the orange color atoms can move to the position D and. What is the effect of left hand side and right hand side? What is the effect of onto the metals on the left hand side to right hand side? Left hand side, this space here is stronger than here. Because here you have additional atom to block any resistance or any force from you press here. This one will block here, so it will stop the forces. If this one moves to here already, this area becomes stronger, and this one stronger impact. Okay, so if you press here, this one is more easier to press because of space here. Press here, this one will combine, not combine, but move shorter. But here, if you press here, this one will move here, but this one can only move a certain distance. Right? So this is how you strengthen them. So again, there's a diagram for you to explain interfacial diffusion. Just draw left hand side before and after. Okay, this is before diffusion, after. So there is a diagram. It's a diagram for vacancy mechanism and interfacial mechanism. right, it's how to join. Okay, so the differences is without permanently displacing any atoms in matrix for the insertion. Insertion, you do not replace any atoms by just moving from one space to another space. One keyword there is diffusing atoms. Diffusing atoms must be relatively small compared to the matrix atoms or the source atoms. It is interstitial. So there will be a question in section C to ask you explain why this is an interstitial or vacancy. You do analysis. For example, this PCC, you ask you this mechanism is suitable. Let's say it give you atoms A, atom B. It give you atom A, atom B. To ask you which one is this, which substitute, which mechanism, diffusion mechanism is suitable for this substitute. You're given info A, info B. So you need to explain why it is vacancy or why it's. So for insertion, there are some popular answers. Hydrogen, oxygen, nitrogen, oxygen. These are the four popular methods or elements that we usually use for presentation. Another one is nickel. Nickel is very important. That's why your stainless steel, almost of your titanium, they will have nickel alloy somehow, nickel and something. Now this graph is more on the steady state distribution. So y-axis is the concentration. In chapter 4, you already learned how to calculate the concentration, right? So just a recap, concentration have two ways of representing it, with percentage concentration and atom percentage concentration. There is a conversion, how to convert this one. So if you forget, please go revision. So concentration here, it can be weight percentage, it can be atom percentage. So distant 1 and distant 2. So let's say you have a solute atom flow. I already explained what is solute and solution. Solid atom flow. So if the concentration drop from position 1 to position 2, it means diffusion happens, like what I draw on that by one. Okay. So if you look at this graph, so over a period of time, concentration of atom at plane 1 is C1 and plane 2 is C2. There is no change in the concentration of the solid atom at this plane for the system in time. So such diffusion condition is said to be steady state condition. So if there's no change of concentration at that plane over time, it means steady states diffusion. So these are diffusion take place when a non-reacting gas diffuse through the vacuous form. So steady states will happen in the gas form. Infuse gas inside there so that the gas will go inside the foil and form. So this one happened in strengthening aquariums, especially nowadays infuse atoms in your microchips. Also your phones, lots of sensors. So if diffusion systems show no chemical reaction occurred between solute and solvent, okay, we already explained what is solute and solvent. Because there is a concentration difference between plane 1 and plane 2, there will be a net flow of atoms from a higher concentration to lower. Right? So you know that in chemistry, if concentration 1 is higher than concentration 2, concentration 1 will move to concentration 2. This is the chemistry flow. Okay. So one of the example, go to temple, burn a candle with just a rope or something, a candle. You put your candle here, and maybe the oil is below. The oil will move up because of the concentration difference. So, to give you the third equation for today, it's called flux or flow of atoms. Given mu by J equal to minus D, and there's a differential equation here, dc over dx. dc over dx is the rate of change of the concentration compared to the direction. Okay, so dc dx is actually from C versus X graph. Is your M graph. It's a gradient of the graph. J is a net flow atoms. So J, it gives you negative. If you see from the graph here, the graph is give you negative gradient, negative D, dc, X. Okay. So if the question asks you or forces you to use Fick's first law of diffusion, you need to write this equation. So the unit SI is J is atom per meter square second. D diffusion is meter square over second. Meter square is area over second. Means you look at the plane of diffusion. Plane of diffusion, how many atoms can move past the surface? Meter square over second. dc over S, this is the radiant of the graph. T versus X graph, the one you see on the screen here. All right. C concentration. Concentration is atom over meter cube. dx is meter. So if you multiply this one, cancel the square, you get the one. This is called dimensionless analysis. So these are the table. They give you different temperature, 500, 1000 Celsius. The diffusion rates. What is diffusion? Diffusion is this one. The E value. You see this table. Most very high chance you'll be tested this Fick's first law. J equal to minus D is C over X. So we have diffusion D value. Okay. I only need to highlight the negative sign in the calculation. 10 power negative something. And diffusion value is negative. Remember to put it on negative in the calculations. Okay. J into. Okay. So there are a few factors you need to consider when you calculate the Fick's law. First is type of diffusion. Type of diffusion, again, type of diffusion, there are two types of diffusion mechanism, either insertation or substitution. There are two types of insertation and substitution. Right? If it is insertion, then we refer to the small atoms. For example, carbon diffused with PCC lattice, right? Carbon in PCC. Okay, now how to use this table? This table already tell you what is solute, what is solvent. So this table, you need to read carefully. The question will tell you what element mixed in what element. So if the question say carbon in metal, you put carbon inside, correct? you use the first, you refer to this table, you use carbon fit into ion. You use this the first row. Okay, at 500 degrees C. If you use copper, silver also. So this one, copper, what does it mean? If you use copper and copper, it's a self-diffusion mechanism. It's a self-diffusion. Okay, and that's the brief. The second one is temperature. First is diffusion mechanism, either is interfacial or substitutional. Second is temperature. So as you can see, the diffusion rate increase when you change the temperature. Change the temperature. The third one is type of crystal structure in the solvent lattice. Okay, so these are the factors when we use the Fish rules, how it affect the diffusion rates. Normally, you'll see this one in the appendix for your assessment. So this is just a reference material for you to answer section A type question. Explain what are the factors that you need to consider for diffusion values. Right? First is diffusion mechanism. Second is the temperature. Third one is the crystal structures. Fourth one is any effect present in the crystal. The first one, the fifth one is concentration. Higher concentration of the diffused solute atoms will affect the diffusion. Okay. So this one also another popular table when it comes to assessment. So diffusion species host metals, the V value, diffusion coefficient, activation energies, and calculated values, Tn. All right, let's look at example 2, then we can go. Okay, a plate of iron is exposed to carburizing process, carbon-rich atmosphere on one side and decarburizing atmosphere on the other side. If the condition is steady state achieved, calculate the diffusion flux of carbon through the plate in concentration of atom and position of 5 and 10 mm beneath the carburizing surface are 1.2 and 0.8 kilogram of flux. Assume diffusion coefficient of 3 negative 10 power negative 11 m square over second at this temperature. So here we have an ion exposed to carburizing atmosphere of carbon rich. So which one go to which one? Which one is solvent? Which one is solvent? We have iron and carbon. Which one is solvent? Which one is solvent? What do you do? So iron is solvent. Then what if I solvent? What do? There's no water here. I think it's a story that I also had which one is solvent, which one is solvent. Right. So I straight away go to the solution. So if you see this kind of question, very obvious. If you see the diffusion coefficient is a piece rules, where you write J equal to minus B C over dx. So you need to calculate the change of concentration dC over dx. So dC over dx is graph concentration over x. So you are given the two value inside the statement. Concentration 1.2, 0.8. Right. Then the position of x from here. So CA is 1.2. Concentration at A is 1.2. B is 0.8. X is 5. XA is 5. XB is 1. 10 power 2. Here, 5 mm and 10 mm. So substitute this one, D is given to get J equal to 2 point something kilogram over plus square meters. Okay, problem is the unit. So if you just calculate without the unit, you only get half of the answer. Okay, so here, stop here. We continue 11:50. Right? 11:15, 11:115.